All right, so welcome to Solutions to AP Review 7. We have two problems where we have objects falling, potential to kinetic. In one case we collide, the other we go off a table and have projectile. The important theme for these solutions is the thoroughness of the derivations. Okay, just to get 1 point, you might have to make three statements. A loss potential goes to kinetic, and then show the equations. So make sure you're fairly thorough here. And again, some of these you have to write them in paragraph form, so you got to learn how to make your sentences, translate what I'm doing kind of like bullets into actual statements. All right, and then also take a look at the PDF to see how things are broken down to get a better idea. Okay, so in the first case we have two cars of different masses, different heights colliding, and they stick together. So that sticking together is important. All right, and the first question asked is which way will they move after they collide and stick? So how do you determine that? It's not about which one's moving faster. It's not about which one has more mass. It's not about which one has more kinetic energy. It's about which one has more momentum. So you have to figure out which one has more momentum. To do that, you have to know how fast you're moving at the bottom. To get how fast you're moving at the bottom, you have to use conservation of energy. So there's a bit involved in the 3 or 4 points that you have on this one. So let me break that down. Okay, so I'm going to show you a different way than the AP shows you because I think in the end it's easier to do. You don't have to do it this way. I wouldn't necessarily expect you to do it this way, but I want to remind you of a nice relationship that we derived that relates kinetic energy to momentum. All right, and that's p squared over 2m. So since we want to figure out the momentum of them, let's just translate that to p, and I'm just going to do it all in one step, is square root of 2 times the mass times the kinetic energy. Okay, so we're going to come back to that later. Now, let's figure out how to get the kinetic energy for each one. So let's do A and let's do B. Okay, so you should make clear that in A, right, the kinetic energy, you could say the change, but it equals the loss in potential energy, which for A, I believe is, falls a big height, so it's a m times 2h times g, which is simply 2mgh. Okay, and for B, right, same idea. I'm not going to write the UG. That's going to be 2m falls only h times g, so sure enough, we have 2mgh as well. Now you might be tempted to say, well, if they have the same kinetic energy at the bottom, and that they're not going to have necessarily the same speed, and they have different masses. So we're going to be careful how we apply this equation. So let's now apply this equation over here. So we got PA, right, is going to be equal to, all right, square root of 2, right, there's the 2. What's the mass of A? The mass of A is m, so I'm just going to leave it as m, times the kinetic energy, which is 2mgh. How does that compare to B? I'll do it down here. PB is going to be 2 once again. What's its mass? If we go back and look, you see that's a mass of 2m times 2mgh. And so we should see that B is greater than A. Therefore, it's going to move in the direction that B is moving, which I think is to the left. Okay, so that's quite a bit to do on that problem. Now things get more interesting conceptually. So now I say consider the time interval from when they're released to when they, just after they collide. And you're going to talk about two different systems. The first system is when we include the Earth and 2 carts, and the second system is just the 2 carts. And they're asking, does the total, and this is important you read carefully, mechanical energy. So mechanical energy is potential and kinetic combined. All right, that's a generic term we have used before, and that should give you a clue as to how we're going to approach the answer. So in this case, you have to make explicit the total kinetic energy, the total mechanical energy is going to decrease. Okay, why? Well, you should make a statement, some statement in words, that the loss in potential, right? The delta potential for either car equals, I'm going to put a negative there, the gain in kinetic. Therefore, and this is the ultimately the total mechanical energy, sigma E, does not change. So even though there is a transformation from potential to kinetic, the overall mechanical doesn't change by rolling downhill. However, where do we come decreases? And so you need to make, and I'm not sure how explicit or proof they want you to give here, because it's only 1 point for this. This is a 2-point problem. This is the first point, is that the total sum of the kinetic and potential doesn't change. Is that in an inelastic collision, that's where the stick together matters. Inelastic, you always dissipate energy. You lose energy, you lose kinetic energy. I can't remember how to spell it. Okay, you dissipate it to thermal. Okay, you don't have to use the word thermal, but you need to make a statement that in inelastic collisions you lose kinetic energy to the environment. I don't expect them. I wouldn't expect you to show the total energy, total kinetic energy before the collision, and then show it after based on velocity. That's a lot of work to show from 1 point. So I'm guessing that it's okay to make the statement that inelastic collisions, because they stuck together, makes there a loss of kinetic energy, because that's the definition of that. All right, now let's go to the case where we just include the carts. In other words, we take away the earth. So in this case, the answer is the total energy mechanical increases, because at the beginning, if we include the carts, there is no potential energy. Okay, potential energy only, gravitational potential energy only exists if you have the earth involved as part of the system. So you would make the argument that at the top, on the ramps, right, there's no energy. They're not moving. Okay, I'm just going to put NRG. And at the bottom, they have kinetic energy. Even if they collide and dissipate some, they still have kinetic, some energy. So they have kinetic at the bottom. And you need to make clear where that kinetic came from. Okay? Kinetic energy at the bottom. Why? Not because of lost potential, because remember, there's no potential at the top because work was done on it by gravity. Gravity in this case is an external force. So it's very easy to overlook that point. We're just so used to saying when something falls, potential goes into kinetic, but we need to make clear why that's not the case here because of how we defined our system. So that's a bit of a problem. It's easy to not get full points for that. Okay, what else do we have on that? All right, so that's it for 1. So let's look at the next problem. All right, so now we have a ramp where we can adjust the height of the ramp versus the table. Okay, so H1 can be raised or lowered, and so if H1 goes up, H2 goes down, such that they must always add up to the total height. And then the block roll or slides off and goes a distance d, and we know projectile motion. So make sure you have your understanding of projectile motion equations. And I'm going to say right now, it's not good enough for this to have the key equations written down. You're going to actually have to derive them. So when I say derive, you make sure you derive that and know how you get those equations that you may have written down in your reference tables or your cheat sheet. Okay, so the first question asks, without using equations, okay, explain why making H1 very small would make D small even though H would be large. Okay, so if we have a small this but a tall H2, why wouldn't be? Essentially what you want to say, and this is just for 2 points, okay, see if I can squeeze it in here, is a small H1 leads to a small potential energy. Okay, and then the next statement, that's not good enough. You would say a small, which would lead, you don't have to write that, but leads to a small ke at the bottom. All right, and then your third bullet, which leads to a small horizontal velocity, okay, and a small horizontal, and then lastly, you'd say small horizontal velocity leads to a short distance. Okay, you can't use an equation there, but conceptually you can say the slower it's going, it's not going to go as far. In part 2, they have a big drop, but a small height from which to fall. So here they want to look at a smaller 2. So what you would want to say there is a small h2 leads to less time to move forward. Okay, and less time to move forward means less distance forward. Now they want you to actually derive an equation for that, right? Derive an equation for D that supports that. Okay, so let's do the equation over on a blank sheet. All right, so part 1, right? We want to say, I'm just going to go to the projectile, right? And again, you might have to be fairly explicit here, but we might say that the distance using kinematics is v naught t plus 1/2 at squared. All right, make some statement that a is 0 in a horizontal direction, so it's just equal to v naught t. Okay, so there is your first part. Part 2. Well, now we get to take each one of these in turn. So let's go to the v naught part. I'm just going to put that off to the side. That's what we're solving for. So you make explicit, so the speed at which it comes off table is based on the energy transformation. So you'd say delta UG equals delta KE. Okay, you can put in the equations for each one of these, but I'm just going to go the upshot. So we have radical 2G H1. Make sure you put that H1 there because there's 2 H's involved. For the third one, you want to find the time in the air. That's where you use VTAX or kinematics. So I'm going to put basically H2 equals V naught YT plus 1/2 AT squared. Okay, this is 0 because it's coming off horizontally, so there's no initial vertical motion. So if I solve for time, I get radical 2 H2 all over G. And again, it's important not just to write this, you got to at least show this step here. So now we combine it, and we've got D equals V naught radical 2 GH1 times radical 2 H2 all over G. I believe you can leave it like that, but let's put everything under the radical, because when we do that, we see the G's cancel out, and we're left with radical 2 H1 times H2. Okay, so then in part C, it asks us which part of our derivation, so I'm going to stay on this page, supports our first assertion, which was talking about a small h1. Well, I can see right here, I can point out, make a statement, when a small h1 gives us a small velocity. And then which part of our derivation supports our statement about a small h2? It's this one. You can point out if you have a small h2, you're going to have a small time in the air. And that takes care of part C's 1 and 2. Last question asks, what if we were to take this to the moon? How would D change? Well, now you can use the final solution. You see that G cancels out, so the moon has no effect at all. Okay, so a lot of good derivation there. Make sure you're thorough. You should be well. Ask questions if you have any.